to explore the deep sea. So quite recent, we have something new. So this cost us 4 years. And one of my students, Ray, is also now a professor. He find actually, if we do the soft material in between the solid and the liquid and make them together, they call this a plasticized electrohydraulic. Actually, the plasticized way for material is ordinary use for the chemistry and for the polymer design, especially everybody's shoes. The bottom layer of the shoes almost use this plasticized way to make it. Actually, there are some solutions sink into the polymer. So we find actually by using this way, we can make this soft robotic fish even more stable and can drive it with a lower voltage. This is something we do in the deep sea, in the South China Sea. And how this robot do better than the previous Mariana fish is that it can contain some sensors to detect the height of the what's the height to the depth, the seabed, which means it can have some trajectory design and control. This is so in deep sea, it's not easy to have a controllable trajectory of swimming, and this robot is something one step more we do for more than survive the pressure, but also have some functions. Okay, this is something about the fish. Well, there are also something we interested in the sea. Of course, it's jellyfish. The reason we're interested is think about the jellyfish have 95% of water containing, but it swims well. And a little knowledge we can take home is that actually the biggest jellyfish in the world is quite close to Zhejiang province. It's in the East Sea of China, between China and Japan, close to the Zhejiang province. This jellyfish goes like the size of 2 or 3 meters, huge. You can see that video compared with the divers. But it's use very simple structure to drive, very thin layers. So this one of my students, Xinge and Dina, they collaborate and they find actually they can make a jelly inside 2 thin dielectric membranes, and it's easily controlled. And by tuning the pattern, the driven pattern of voltage, it can go forward and backward without any change of the structure or any change with the tunable motors. So this is something we find, okay, the watery robot can also do something in water. Okay, and we got something very special in stream this year that when we're talking about using some watery material, we think something can survive the temperature. Is very hard because if you go lower than 0 degree, the water goes to ice, it freezes, and it goes to over 100 degrees C, it becomes vapor. Can any creature survive that? So one thing, even in some websites or some WeChat, there are very popular creature, tardigrades, but we think the tardigrades is not good enough. The reason is that how it suffers the temperature is that it basically goes to the hibernation, which means the water goes out and then it can suffer the low and high temperature. Is there any creature that contains water also can suffer the high and low temperature? This is actually also from the deep sea. That's why I'm talking about deep sea. So in the deep sea, actually, there are some volcanoes we call these thermal vents. So which means close to the vent, there are some like tube worm. The temperature goes deeply to like over 100 degrees C. And just a little, like 1 centimeter away from it, it goes to 2 or 4 degrees C. We don't know much about this creature, but we know something about the materials. So they are fully sulfuric materials. And what we do, this is quite recent. I think it's a material, but I'm quite like to share this with you, robot expert, because we build this material and we haven't used this material for some robots, which everyone is welcome. If you have new ideas, we will tell you how to make these materials. Basically, we have a jelly like a tofu, but this tofu is very special. It's sulfuric produced tofu, and it suffers the temperature over our common sense. So it contains water. If you go to, it's very soft, and water containing is at over 15%. Half of it is water. But even you go to the -80, it's still watery and soft, no freeze. And even you go to 140, so normally the water, of course, will become vapor, but it also sustains the temperature. It's still soft and watery. And why we think it's possibly can do something with robots, because it can, this very watery and super low and high temperature, of course, we're talking about the water, -100 and over 140. This is not like this extreme temperature for metal, but for water it is. It can use as a flexible sensor. So that's why we want to show this quite new recent progress, but we are not designing this material for some special robots, but we believe the idea we have is limited. So everyone is welcome. If you have an idea, if you want to use a soft material for robots, watery, and goes to extreme temperature, we are super happy to show you how we make these materials. And we wish this can be some new candidates for the soft materials, robots. And finally, we go to more interesting, and because I'm a mechanics guy, so one of my students called Zhikun, and a member in our team, Fang Hao, they have a design that they want to make some swimmer. We're talking about swimmers. They build a swimmer, very tiny swimmer driven by ultrasonic source. And how they control this? Only by tuning the frequency of the ultrasound, that's all. And how it can turn and it can move, it's all because of this geometry design. And it's super simple and robust. And it even have a clap, like the claw of the crab. And this is also driven by ultrasonic single source. We are not talking about you have many sources and you have the independent contractuators. No, it's all only one piece, two photo lithography printing. You only have this structure design, and you only have one source of the ultrasonic. The only thing you can do is tuning the frequency. The idea they have is it is asymmetric, so which means different tails have different natural frequency of resonance. So then you can move it left and right. So how it works, I will mainly show the idea and the video. So how the gripper claps is because if you using the ultrasonic actuation, the fluid pressure in between will become a low pressure zone. So the claps will close. So we can grip some little bits. And how it swim, I will go to the next. Because it have two different sides of the tails. So the two different lengths of the tails have different natural frequencies. So which means if you tune the frequency of the ultrasonic source, it goes left and right. So, and what's the function of this one? So we can a little bit manipulate with some microorganisms. So this is little organisms, microorganisms, and you have setting up a trajectory, and you grip it and move it to the target. So for this micro manipulation, it's not like the very precise, or even you have the ultrasonic tweezer to do this, but we find this structural design and one-piece design, the idea is important. So something swimmer can be one-piece printing and without any independent actuation, just by geometry difference. And you have a single source control. This is something we believe can be applicable in some extreme tasks, especially in some small size, but you cannot install many devices. The installation is limited. So this can be something interesting. Okay, so finally, this is a paper coming soon. I believe maybe in this year, this recently just get accepted in Nature. The idea is that for the geometry design, we human beings actually already record information. Everyone knows information is very important for robots, which means the sensing, the control, and the further means think about it. So like 5,000 years ago, people making notes to writing, making their something important record. So the idea we have is, can robots also use a single rope with knots to record the force? To record the force means it's possible to maintain force or to control force. What we find is actually everyone is doing this every day. If you tie your shoe, I already saw in some workshop they are talking about using the robot to tying the shoe. So if you have a slip knot, we actually find it's very interesting. When you open up a slip knot, there is a snapshot, and it will have a very precise F peak, which means if you the slip knot goes released, the F peak is very precise. How precise it is? Of course, we do a lot of mechanics study. I will pass the details because we write everything in the paper. We find actually this is controllable and programmable. So which means this little slip knot can be a mechanical force sensor. It's not closed loop, but it can be precise control. So, and the consistency is very high, and we use a very simple topological based model to describe it. So when we find this one application, the surgeons are very interested in this because they are doing the suturing every day. Especially they are doing the suturing for the intestine. It's very important to control how tight the suturing is. But you know, even for some robotic surgery, it's not easy to sense the tightening force. Otherwise, you need some, a sensor. So we work with many surgery robots, including Da Vinci. We find the surgeons don't need to add any devices. The only thing they need to do is make a tie, designed tie for their suit during their suturing. So there are nothing more for the surgery devices, and it's very controllable. So I believe that's why the Nature like this idea. So we make this slip knot as a sensor. It's nothing electronic, fully structured and geometry based. So, and we have the mechanics model, and it's very reliable. This kind of out of our imagination. We think, okay, mechanics model somewhat can be comparable, cannot be precise, but the result shows out it is precise. So, and even more interesting that this doesn't matter with the scale. We have the study for the DNA, like the nanometer size of chain. You go like micro thickness of the wire, and you go, of course, you can do it with your tying shoe. And we find a very big rope that rope is using to find the huge shape in the port, and we use some hydraulic huge arm to doing this type, and it is very consistent. All have this F peak, and it's controllable and programmable. So we believe this can be further. Of course, this is a simple idea, and we believe this is something ideal that can import in some robotic, especially structure-based design. So the force control doesn't mean it has to be an electronic-based device. Sometimes a structure itself is some force control contained inside. Okay, I think that's my talk. And what we do is something about the physics and some bio-inspired, and we do mechanics and machine. And this video I want to show you guys is during one deep sea experiment. You see the soft robots, the rigid robot, but most beautiful is that a little shrimp, colorful shrimp, and deep sea, and he swims way better than us. Okay, thank you.
Okay, thanks Professor Lee for your talk. And any question for the robot and the talk? Yeah, please.
Okay, thank you, Professor Lee, for your impressive presentation. So I have one question about, because you talk about the extreme environment, extreme like the condition for materials. So my question is, so you talk about like the very freezing temperature. So if it's possible, like put this material, like the hydrogel, to a very high temperature and make a new robot like for the Vagno or other extreme environments.
Yes. I will first talk about the low temperature. Many groups, especially in medicine and some biologists, already in contact with us, because for them it's very important to preserve some living cells or living organs under very low temperature. But to deal with the freezing of water is one of the challenge they have. So now they want to use our strategy. Of course, we the paper published using the sulfuric acid. This is not good for living cell, but already have some more biocompatible contents of the material. They want to use this as the matrix to load some cells or organisms in. They have actually the biologists also have the idea of cyborg. They want to use a robot, small robot together with some cells. So this is one thing we believe can do. And for the high temperature, this is something we still don't have a good idea. But one thing we believe we can do is to some field exploration place. For that thermal vent, this is something we want to do. So because this is some undersea, we already have some this vent. If some robots was contain and can claw into this thermal vents, we believe it will be something interesting. Okay. Thank you.
Okay, any more question? Then maybe I have one question, because about deep sea robots, about the rigid one, they can just go down to the deep sea. But for the soft one, maybe most of them are first taken by the rigid robot to go downside and then do some manipulation tests.
Yes.
So what do you think is the biggest challenge to let the soft robot to from the surface to the sea?
Yeah, a very good idea. A very good question. So we believe the soft robot for deep sea exploration is more like a probe. So we believe most of the deep sea robots or the engineering structures or device rigid is actually very good. So you have very large load and easy manufacturers. But for this, for example, because we always collaborate with the in the sea exploration mission, they have big robots and big device, but it's very dangerous for them to get close to this thermal vent, because it's very dangerous. Because normally that kind of device is using the anti-pressure shell rigid. So for anti-pressure shell, if they get have a collision, it's very dangerous. It possibly have a collision, have a little defect, and then you will collapse. So what they do, that normally like keep distance to this thermal vent, and I believe that is the chance for our soft robot. So for the soft robot we have in this, also in these slides, actually it basically have a big robot, rigid robot at their base or at their carrier. So the big one always carry like 5 or 6 little ones, like a little probe, to get close to the dangerous zone. And they just make a circle where they have many circles and get the data and come back. Even they cannot come back. This is actually something we are working on now. We are designing some materials can be digested by the environment. So the informations come back. Even the robot itself have something, have a failure. You just okay. Its mission is over. It's yeah.
Okay, thank you for your thank you for your answer, and thanks for the talk. Thank you.
Okay.